So today I will discuss about closed immersion, and I will discuss about the criteria of closed immersion. Okay, first let me recall. Uh, Let f from x to y be a morphism of pre-varieties. Then f is called a closed immersion if uh, there exists a closed sub-pre-variety z of y and an isomorphism of pre-varieties g from x to z such that the following diagram commutes. X to y we have this f, x to z we have this g which is an isomorphism, and z to y this is inclusion map, and this is a closed sub-pre-variety. So this diagram commutes. So this was the definition for closed immersion. Okay. Now let me state the criteria for closed immersion. Proposition. This is actually criteria of closed immersion. Again, let f from x to y be a morphism of pre-varieties then the following are equivalent. Number one is f is a closed immersion. Number two is for any affine open subset U inside Y, F inverse U is affine and this OIU to OX F inverse U, this is surjective. Okay, a double arrow means surjective. And number three is there exists an affine open cover of X, say UI, I belongs to capital I index set, such that F inverse UI is affine and this OI UI to OX F inverse UI, this is surjective. This is true for all I. belongs to capital I. So this is the proposition, this is the criteria of closed immersion. Now proof, let me prove this. Proof, first 1 implies 2, 1 implies 2. So it is a closed immersion means we have this, that F is a closed immersion means we have a G isomorphism from X to Z, and this is inclusion. This is closed subprevariety. Okay. So for proving this part 2 means we have to show that for any affine open subset U, F inverse U is affine, and OIU to OX F inverse U, this is surjective. So it is enough to show that if U is affine open subset of Y, then U intersection Z is affine, and this OIU to OZ U intersection Z, this is surjective. Okay. So this is what we are going to show. Now what is the structure shift on Z? For V inside Z open, the structure shift of Z, this OZ of V, this is nothing but the pullback of this shift, structure shift of on Y, right. So this is nothing but, if you remember the definition of this pullback, so you can see that this is all those maps from V to K such that for every points inside V there exists a open set inside Y containing X, say Wx, and morphism, say psi x, from Wx to K. This is morphism and this is regular function, such that this Wx intersection Z, this is inside V, and this psi x restricted to Wx intersection Z is equals to phi restricted to Wx intersection Z. It means that this phi, this function phi from V to K, this is locally regular functions. Okay. So fine. Now so we have this, that U, this U intersection Z, this is inside U. Now U is affine, and U intersection Z, because Z is a subprevariety, closed subprevariety. So in the definition of prevariety, we also assume that it is irreducible, right. So U intersection Z, this will be irreducible closed subset of U. and U is affine. Okay. Now exercise. I am not going to do this. It is easy. This OZ of U intersection Z, where this U is this U and Z is the sub prevariety of Y, and U is a affine open subset of Y. Then this is actually equals to all those morphisms, not morphism, functions from U intersection Z to K, such that there exists a psi from U to K which is regular, such that psi restricted to EU intersection Z, this is equals to phi. Okay. So this is an exercise. For doing this exercise, you need to consider the in an affine variety, you need to consider those basic open subsets of the form D of F, and you have to consider their ring of regular functions. Okay, which is actually nothing but the localization at that regular function. So fine. So from here it says that I of U intersection Z, which is all those regular functions on U, such that those regular function all those regular functions such that they vanish on every point inside U intersection Z. Okay. Now because U intersection Z is irreducible closed subset, so this is a prime ideal. This is a prime ideal of OIU, and this OZ U intersection Z, this is isomorphic to OIU quotient by this I of U intersection Z. Okay. So this is easy to see, right? Now from here, this implies that OZ U intersection Z, this is a finitely generated integral domain over K, since this OIU is a finitely generated integral domain over K. Okay. So this implies that this U intersection there Z, this is affine, and this OIU to OZ U intersection Z, this is actually a surjective map, surjective K algebra homomorphism. Okay. So then this first part is done, means 1 implies 2, this is done. Now 2 implies 3, this is obvious statement. If it is means true for every affine open, then it is true for every affine covering, right? This is obvious. So now the 3 implies 1, this part. For this, so X is a affine open, this UI is an affine open covering of X, affine open cover. Open cover, and we know that this F inverse UI is affine, and this is surjective, right? The OI of UI to OI of F inverse UI, this is surjective. So these things are given. Okay. Now consider for each I, consider this I, say ideal of I, ideal, okay, this I is an ideal defined by, this is the kernel of this morphism, this surjective morphism. Okay. So this is kernel of this surjective morphism. So now define this Zi to be this V of this this ideal, means this is nothing but the 0 set, 0 all the points inside ui such that h of x, this is equals to 0 for all h inside this ideal. Okay. So these are the elements of this this ideal, they are actually regular functions. So all the common zeros, all the all the common zeros of this of the regular functions inside II, means this ideal, this we denoted by Zi. Okay. Now and also define Z to be this union of this Zi. Okay. Now I am not going to do it, means all the, means if you use all these informations, just I will give it as an exercise. Check the rest of the details, means what you have to show, means this is the Z, means you have to show that this x to y, this map, this factors through this, there exists a G you have to show, which is an isomorphism, and you have to show that this is the inclusion, this is the closed subtree variety. So this part is just easy verification, you have to do some easy verifications. Now now let me recall another thing. So we are done here, this proposition, the criteria for closed immersion, that it's done. Now recall graph of a morphism. Let f be a morphism of pre-varieties, Okay. So we know that this product, this exists, and if we consider this maps x to y, this is f, say, and this is, say, x to x, this is identity on x, then there exists a unique map, say we denote it by, say, jf, from x to x cross y, such that this diagram commutes. Okay. So this x, this map x to x cross y, this takes this jf, this takes small x to small x comma f of x. Okay. And the graph is defined as this image of this jf inside x cross y. So this is called the graph of f, this morphism. Okay. So now the proposition is this jf this is a locally closed immersion, locally closed immersion. Okay. So this is easy, again the proof is easy. Now choose and choose affine open covering, affine open coverings of x and y, covering of x and y, say x is ui union of ui, these are all affine open subset, and y to be union of vi, such that the f of ui is inside vi. So this kind of covering is possible. We are not assuming that not necessarily all vi are different. Okay, then it is possible to find such covers such that f of ui is inside vi. Okay. Now consider this J inverse of ui cross vi. This will be, this is actually nothing but ui. If you see this diagram, then it is pretty obvious. Now, so we restrict this map, this Jf at ui, then this is a morphism from ui to ui cross vi. Now, if you remember the how we constructed this product of two varieties or two pre-varieties, we we took affine open covers, then we took the product of two affine varieties, then we do some gluing, then we got the product of two pre-varieties, right? And the product of two affine varieties, it comes from the tensor product of two the corresponding coordinate yes, coordinate rings. Okay, right. So here we are going to do the same thing. Now this morphism, so its corresponding K algebra homomorphism is this O of ui tensor O of vi, this is tensor over K to O of ui, right. Now this is given by A tensor V, this goes to A times this F star upper star B. What is this F upper star B? This F upper star B is where this F upper star B is nothing but this morphism from OY to F lower star OX. Okay. So now this is surjective. This is surjective, right? It is pretty obvious. Means because A tensor B goes to A times F upper star B, right? So if you it is easy to see that it is surjective map. Now let this U to be we define this U to be union of all this ui cross vi. So this is open inside x cross y, and now if we use the previous criteria for using the criteria criteria of closed immersion of closed immersions immersions. We have this JF. This is from X to this U. This is closed immersion. This is closed immersion, and this U, this is actually open inside X cross Y, right? So this composition is the locally closed immersion, locally closed immersion. So we are done. So we see that this JF, this morphism from X to X cross Y, which takes to the means whose image is the graph of the morphism. This is a locally closed immersion. So okay, let me stop here. Thank you.